Welcome to lesson 6.8. In this video, we're going to be focusing on trapezoidal approximations. In the previous lesson, we talked a little bit about Riemann sums, and in doing that, we took either the right or the left or the center, and we created rectangles that we used in order to estimate the area underneath the curve. When we look at it, though, you'll notice that there's a lot of extra space on one side or the other. You probably noticed that. And while some of them may be pretty accurate, the rest are not as accurate as you'd like. And so in the effort to try and make the information we're estimating as accurate as possible, another way to approach it is by using a trapezoidal approximation. Keep in mind that a trapezoid is typically we see it like this, where you've got your parallel top and bottom piece, and then you've got angular sides. We typically find the area for a trapezoid by taking the top and the bottom, adding them together, and then dividing them by a half, and then multiplying that by the height. This is the formula that you're probably pretty familiar with. What we need to do, though, for our functions here, in order to use the trapezoid as an estimation tool, is we need to flip it up, flip it 90 degrees, so that we're looking at it with the width where the height used to be. And so we're looking at a fixed width with two variable heights and an angle at the top. And we would still use the same basic formula. Our area is equal to 1/2 our width, only in this case it's our heights that are added together and then divided by 2. And so if we looked at or considered our one of the graphs that we used before, if we just took each of these individual pieces here, if we went from 0 to 1, if we used the 0 point as side as 1 point and the 1 side as another point, then in this case it looks more like a triangle, but we would have a much more accurate picture here than if we were to make this an actual rectangle. Same thing from 1 to 2. If this was our 1, this would be our 2. We make our angled piece right here, and we could solve for the area underneath that function much more accurately than we could by simply using it as a square, or as a rectangle, sorry. Okay, so let's take a look at how this actually works and run a few examples. So our first one here, we've got this function. In fact, this function should look suspiciously familiar to the one on the other page. And basically what we're looking to do is identify the areas, of the trapezoid areas that they've given us here. We've got 5 sections, and in this case, each of the sections are different widths. That's okay. But we're going to use the trapezoids to estimate our integral, the value of our definite integral. So we're going to start off with proper notation. This is going to go from 0 to 10. This is our f of x dx. And we're going to say that it's approximately equal to these trapezoids that we're going to add together. So if we take our first trapezoid here, number 1, this is going to be 1/2. Okay, our width now is going to be 2, from 0 to 2. So our width is 2. And the height on one side is 0. And we're going to add to that the height on the other side, which, if we follow it up, is 4. Okay, so that's the first one. We're going to add to that now the second one, which is from 2 to 5, it looks like. So we've got a width of 3. And our heights are going to be 4 on one side and 3 on the other. So 4 plus 3. Okay, that's 2 down. Next one's 1/2. Our width here is 1. It's going from 5 to 6. So 1. And then we are looking at the height on the 5 side, which is 3. Height on the 6 side, which is 2. So 3 plus 2. Trapezoid number 4 actually looks like a rectangle, and in this case it is. So on the 6 side we've got 2. On the 8 side we've got 2. Our distance between them is also 2. So this ends up being 1/2 times our width, which is 2. And the height on the 6 side is 2. And on the 8 side is also 2. Our final one here, trapezoid number 5. Start off with our 1/2. This is going from 8 to 10. So our width is 2 units. On our 8 side, we've got 2. On our 10 side, we've got 5. And if we added all of these things up, this is our estimated, the estimated value, of this function underneath this graph. Okay. Again, this is a trapezoidal approximation. This will give you a little more accuracy in many cases than the Riemann sums will, although it's still not super accurate. Okay, one more example here. If we were to take a look and do this same graph, or a similar graph, but all we were given was a table. If you notice each of these units here, we've got from 10 to 20, 20 to 30, 34. You notice that the width on all of these is going to be 10. So even though we don't have a graph associated with this, we do have a table, and so we can use that table to create our estimation. In this case here, I don't have an actual function name here. We could call it anything, or we could simply call it the area. So in this case, the area of this graph is going to be equal to, and then we can take a look at the variety of trapezoids that are formed. So we would start from the smallest to the largest, going from left to right. And so our area is approximately equal to, I need to make sure I correct that, approximately equal to, start with the first one, 1/2. We know that the width between these is 10. In fact, the width between all of these is going to be 10, so that'll make it easy for us to write. The one at 10 is 1.8. We add to that the one at 20, which is 2. Okay, go on to the next section here, 1/2. Our unit is 10. This time we're doing 20 and 30. So at 20, we're at 2. At 30, we're at 2.5. Next section is going to be, again, 1/2. Our width is going to be 10. These are all uniform widths. This is going to be from 30 to 40. So this is going to be 2.5 plus 3.5. And our final piece is going to be 1/2 times 10. And this one's going to be 3.5 to plus 2.2. Okay, we don't actually know what this graph is doing in between these, but we can say that given this table, the area underneath it is going to be approximately equal to this value here. Now, I'm not going to go ahead and calculate this in. I hope this is something that you can do in the calculator pretty easy. And so I'm not going to spend the time going over that right now. You could also, however, with this one, if you decided to lump it all together, you could, and this might be easier for a calculator, you could potentially write this as like this, 1/2 times 10. And since that's common to all of these, then you do your great big parenthesis, and then you would do your individual sections one at a time. And all you would be worried about is the y values for each of the two sections. And so in this case, we've got something that looks like this. So this would be an alternative way of writing it. You need to make sure you get the correct y values when you're putting this together. And if you're putting this in the calculator, again, it looks a little bit shorter. Basically, you factored out the 1/2 and the 10 from each of these.